Hello friends, after having a detailed look at the Maxwell's relations in the earlier lecture and learning that they have far reaching implications in thermodynamics and are frequently used to derive useful thermodynamic relations, we now move on to the next important topic, the Clapeyron equation. The Clapeyron equation is one such relation which enables us to determine the enthalpy change associated with a phase change, such as the enthalpy of vaporization, from a knowledge of P, V and T data alone. Consider the third Maxwell relation, partial derivative of P with respect to T keeping V constant is equal to partial derivative of S with respect to V keeping T constant. During a phase change process, the pressure is a saturation pressure which depends on the temperature only and is independent of the specific volume, that is, P saturation is equal to F T saturation. Therefore, this partial derivative can be expressed as a total derivative dP upon dt saturation, which is the slope of the saturation curve on a PT diagram at a specified saturation state. This slope is independent of the specific volume and thus it can be treated as a constant during the integration of the third Maxwell equation between two saturation states at the same temperature. For an isothermal liquid vapor phase change process, for example, the integration yields Sg minus Sf is equal to dP upon dt at saturation into Vg minus Vf, or dP upon dt at saturation is equal to Sfg divided by Vfg. During this process, the pressure also remains constant. Therefore, from equation dH is equal to Tds plus Vdp, we get integral of dH from F to G is equal to integral of Tds from F to G, which gives Hfg is equal to Tsfg. Substituting this result into equation A, we obtain dP upon dt at saturation is equal to Hfg divided by Tvfg. This is called the Clapeyron equation after the French engineer and physicist E. Clapeyron. This is an important thermodynamic relation since it enables us to determine the enthalpy of vaporization Hfg at a given temperature by simply measuring the slope of the saturation curve on a PT diagram and the specific volume of saturated liquid and saturated vapor at the given temperature. The Clapeyron equation is applicable to any phase change process that occurs at constant temperature and pressure. It can be expressed in a general form as dP upon dt at saturation is equal to H12 divided by Tv12. Here the subscripts 1 and 2 indicate the two phases. The Clapeyron equation can be simplified for liquid vapor and solid vapor phase changes by utilizing some approximations. At low pressures, Vg is much greater than Vf and thus Vfg is approximately equal to Vg. By treating the vapor as an ideal gas, we have Vg is equal to RT upon P. Substituting these approximations into Clapeyron equation, we find dP upon dt at saturation is equal to P Hfg divided by RT square, or dP upon P at saturation is equal to Hfg divided by R into dt upon T square at saturation. For small temperature intervals Hfg can be treated as a constant at some average value. Then integrating this equation between two saturation states yield natural log of P2 upon P1 at saturation is approximately equal to HFg divided by R into 1 upon T1 minus 1 upon T2 at saturation. This equation is called the Clapeyron-Clausius equation, and it can be used to determine the variation of saturation pressure with temperature. It can also be used in the solid vapor region by replacing HFg by HIg, that is the enthalpy of sublimation of the substance. General relations for du, dH and ds. The state postulate established that the state of a simple compressible system is completely specified by two independent intensive properties. Therefore, at least theoretically, we should be able to calculate all the properties of a system at any state once two independent intensive properties are available. This is certainly good news for properties that cannot be measured directly, such as internal energy, enthalpy and entropy. However, the calculation of these properties from measurable ones depend on the availability of simple and accurate relations between the two groups. In this discussion, we develop general relations for changes in internal energy, enthalpy and entropy in terms of pressure, specific volume, temperature and specific heats alone. We shall also develop some general relations involving specific heats. The relations developed will enable us to determine the changes in these properties. The property values at specified states can be determined only after the selection of a reference state, the choice of which is quite arbitrary. Internal energy changes. We choose the internal energy to be a function of T and V, that is U is equal to U TV, and taking its total differential we get du is equal to partial derivative of u with respect to t keeping v constant into dt plus partial derivative of u with respect to v keeping t constant into dv. Using the definition of Cv, we have du is equal to Cv dt plus partial derivative of u with respect to v keeping t constant into dv. Now we choose the entropy to be function of t and v, that is S is equal to S Tv, and taking its total differential we get ds is equal to partial derivative of S with respect to t keeping v constant into dt plus partial derivative of S with respect to v keeping t constant into dv. Substituting this into the TdS relation, du is equal to TdS minus Pdv yields du is equal to t into partial derivative of S with respect to t keeping v constant into dt plus t into partial derivative of S with respect to v keeping t constant minus p into dv. Equating the coefficients of dt and dv in equation A and B gives partial derivative of S with respect to t keeping v constant is equal to Cv upon t, and partial derivative of u with respect to v keeping t constant is equal to t into partial derivative of S with respect to v keeping t constant minus p. Using the third Maxwell relation, we get partial derivative of u with respect to v keeping t constant is equal to t into partial derivative of p with respect to t keeping v constant minus p. Substituting this into equation A, we obtain the desired relation for du as du is equal to Cv into dt plus t into partial derivative of p with respect to t keeping v constant minus p into dv. The change in internal energy of a simple compressible system associated with a change of state from T1 V1 to T2 V2 is determined by the integration of Cv dt from T1 to T2 plus integral of t into partial derivative of p with respect to t keeping v constant minus p into dv from V1 to V2. Enthalpy changes. The general relation for dH is determined in exactly the same manner. This time we choose the enthalpy to be a function of T and P, that is H is equal to HTP, and taking its total differential we get dH is equal to partial derivative of H with respect to T keeping P constant into dt plus partial derivative of H with respect to P keeping T constant into dP. Using the definition of Cp, we have dH is equal to Cp into dt plus partial derivative of H with respect to P keeping T constant into dP. Now we choose the entropy to be a function of T and P, that is we take S is equal to STP and take its total differential as ds is equal to partial derivative of S with respect to T keeping P constant into dt plus partial derivative of S with respect to P keeping T constant into dP. Substituting this into the TdS relation, dH is equal to TdS plus VdP gives dH is equal to T into partial derivative of S with respect to T keeping P constant into dt plus V plus T into partial derivative of S with respect to P keeping T constant into dP. Equating the coefficients of dt and dP in equation C and D, we obtain partial derivative of S with respect to T keeping P constant is equal to Cp upon T, and partial derivative of H with respect to P keeping T constant is equal to V plus T into partial derivative of S with respect to P keeping T constant. Using the fourth Maxwell relation, we have partial derivative of H with respect to P keeping T constant is equal to V minus T into partial derivative of V with respect to T keeping P constant. Substituting this into equation C, we obtain the desired result for dH as dH is equal to Cp dt plus V minus T into partial derivative of V with respect to T keeping P constant into dP. The change in enthalpy of a simple compressible system associated with a change of state from T1 P1 to T2 P2 is determined by the integration of this equation, and we get this result. The Joule-Thomson coefficient. When a fluid passes through a restriction such as a porous plug, a capillary tube or an ordinary valve, its pressure decreases. We have seen in lectures that the enthalpy of the fluid remains approximately constant during a throttling process. You will remember that a fluid may experience a large drop in its temperature as a result of throttling, which forms the basis of operation for refrigerators and air conditioners. This is not always the case, however. The temperature of the fluid may remain unchanged, or it may even increase during a throttling process. The temperature behavior of a fluid during a throttling process is described by the Joule-Thomson coefficient, defined as mu is equal to partial derivative of T with respect to P, keeping H constant. The Joule-Thomson coefficient is a measure of the change in temperature with pressure during a constant enthalpy process. Notice that if the Joule-Thomson coefficient is less than 0, temperature increases. If it is equal to 0, temperature remains constant. If it is greater than 0, temperature decreases during a throttling process. A careful look at its defining equation reveals that the Joule-Thomson coefficient represents the slope of H is equal to constant lines on a TP diagram. Such diagrams can be easily constructed from temperature and pressure measurements alone during throttling processes. A fluid at a fixed temperature and pressure T1 and P1, thus fixed enthalpy, is forced to flow through a porous plug, and its temperature and pressure downstream are measured. The experiment is repeated for different sizes of porous plugs, each giving a different set of temperature and pressure readings. Plotting the temperatures against the pressures gives us a H is equal to constant line on a TP diagram. Repeating the experiment for different sets of inlet pressure and temperature and plotting the results, we can construct a TP diagram for a substance with several H is equal to constant lines. Some constant enthalpy lines on the TP diagram pass through a point of 0 slope or 0 Joule-Thomson coefficient. The line that passes through these points is called the inversion line, and the temperature at a point where a constant enthalpy line intersects the inversion line is called the inversion temperature. The temperature at the intersection of the P is equal to 0 line and the upper part of the inversion line is called the maximum inversion temperature. Notice that the slopes of the H is equal to constant lines are negative at states to the right of the inversion line and positive to the left of the inversion line. A throttling process proceeds along a constant enthalpy line in the direction of decreasing pressure, that is, from right to left. Therefore, the temperature of a fluid increases during a throttling process that takes place on the right hand side of the inversion line. However, the fluid temperature decreases during a throttling process that takes place on the left hand side of the inversion line. It is clear from this diagram that a cooling effect cannot be achieved by throttling unless the fluid is below its maximum inversion temperature. This presents a problem for substances whose maximum inversion temperature is well below room temperature. For hydrogen, for example, the maximum inversion temperature is minus 68 degrees centigrade. Thus, hydrogen must be cooled below this temperature if any further cooling is to be achieved by throttling. So friends, here we come to the end of our discussion in this lecture. Therefore, we sum up. The Clapeyron equation enables us to determine the enthalpy change associated with a phase change from a knowledge of P, V and T data alone. The temperature behavior of a fluid during a throttling process is described by the Joule-Thomson coefficient. The Joule-Thomson coefficient is a measure of the change in temperature of a substance with pressure during a constant enthalpy process. So friends, that is it for today. See you in the next lecture with more on thermodynamics. Thank you very much.